In this video, we will learn about quantum gates. We will list them, we will do their examples. But before going to start that, we must know some of the key facts. Number one, quantum gates must be unitary. Why it is so? Let's see an example. So, I apply a quantum gate on a qubit, say alpha. So, this is my qubit. This is either a single qubit or a register having multiple qubits, and my transform qubits are get beta. This is my transform qubits. We know that the sum of probabilities for qubits must be equals to 1. That means different possibilities of having different outputs must all be equals to 1. So here we know that the sum of probabilities will be equals to 1. But what about this operation u that we have applied on this qubit? This operation u must be special, which preserve the sum of probabilities. That means this operation u must preserve the norm of a vector. And that's why we know that there is only a single type of operation, a single type of matrix that can preserve norm of a vector, which is called unitary matrix. So this must be a unitary matrix, because otherwise we will say here the sum of probabilities equals to 1 and the transform qubit has sum of probabilities equals to 10, which will be wrong. So only the unitary matrix are the types of matrices that always preserve norm of a vector. I have made a separate videos proving some of the simple properties of unitary matrix. The link of that video will be somewhere here, so please watch that video also to become a better scientist. Now, what is a unitary matrix? A unitary matrix is where u conjugate transpose times u is equals to u times u conjugate transpose is equals to identity. So you can say that in this case, my conjugate transpose is basically the inverse. So if I take conjugate transpose of a matrix u, I will get its inverse. Now there is another kind of matrix called Hermitian matrix. For Hermitian matrix, if I take conjugate transpose, then my result is equals to the same matrix. So conjugate transpose doesn't change the result and my result is equals to the same matrix. Let's do an example to make it clear. In this example, my matrix is called Y, and the matrix is 0 iota minus iota 0. Now I have to verify if this matrix is unitary, Hermitian or both. By the way, if a matrix is unitary as well as Hermitian, then it has a special property that in this case its inverse is equal to itself. Because of these two properties, when combined together, we can say for this matrix, if this matrix is A, then its inverse is equal to itself. We don't have to take conjugate transpose, we can just multiply that matrix with itself and we will get identity. And this matrix here is unitary as well as Hermitian. So let's try. So if I take its conjugate transpose, then my answer is that first I take this row and write it as a column. So 0 minus iota, but I also have to change the sign of all the terms having iota because I have to take transpose and also conjugate. And conjugate implies that the terms having iota change their sign. So this iota will become plus iota. Now take this row and write it as a column. I will get iota and 0. Once again, I have to change the sign of all the terms having iota, so this will become minus iota. And now you can see that Y conjugate transpose is equals to Y, so Y is a Hermitian matrix. Now we have to see if this is a unitary matrix. To that end, we multiply Y conjugate transpose with Y, so we multiply 0 minus iota, iota 0 with 0 minus iota, iota 0, and this will be 0 times 0, and this will be minus iota times iota here, and then this will be 0 times this, and then this will be 0. So I will have 0 here, and then here I will have 0 plus 0, so I will have 0 here. In the last case I will have once again minus iota times iota, and this simplifies to 1, and this simplifies to 1. So yes, this matrix is both Hermitian and unitary. Now, after explaining these simple concepts, we can now list the quantum gates. Now we can list some quantum gates. Obviously there are infinite many quantum gates because there are infinite many unitary matrices, and each unitary matrix can be considered as a quantum gate. However, in this video I will write most widely used quantum gates. Let's start with the X gate, which is also known as Pauli-X gate or NOT gate. Pauli-X gate takes a single qubit as input and produces a single bit as output. Like all quantum gates, it is reversible and it is reverse of itself. It is because this gate is both unitary and Hermitian. All the gates which are both unitary and Hermitian are inverse of themselves. Now let's write the matrix of this gate. So matrix of our X gate or Pauli-X gate or NOT gate is equals to 0, 1, 1, 0. Now please note that for a single qubit we need 2 raised to power 1, that means 2 by 2 dimension matrix, because single qubit needs a 2-dimensional vector for its representation, and for 2 qubits we need 4 by 4 dimension matrix, and to manipulate n qubits we need 2 raised to power n by 2 raised to power n dimensional matrix. Now let's see how this matrix operates on different kinds of qubits. Let's say I take my quantum gate X and apply it on a pure state of ket 0. Then it alters the state of the qubit from 0 to ket 1 because it is a NOT gate. Similarly, if I apply it on ket 1, my answer is ket 0. I think a more interesting case is that I apply X gate on a superposition. Let's say I apply X gate on a superposition of alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers and they normalize this vector. So how to find our answer? Now note that all the quantum gates are linear, so we can simply take this X inside the summation and rewriting it as alpha X times ket 0 plus beta X times ket 1. And now we can simplify it easily to alpha, and this will become ket 1 plus beta, and this will become ket 0. So now we know how to apply our X gate on pure states and how to apply it on any superposition. Before exploring another quantum gate, let's verify this thing using matrix and vectors so that our concepts are crystal clear. To verify this, I write X in a form of matrix. So this is my X, 0, 1, 1, 0. And I write my vector alpha get 0 plus beta get 1 in the form of vector. And because here at the 0th location I have alpha and at the first location I have beta, so my vector will be alpha beta. Now I multiply this matrix with this vector to see if I get the same result or not. I multiply first row with column getting 0 times alpha, 0 times alpha plus 1 times beta, 1 times beta. And here I will get 1 times alpha, 1 times alpha plus 0 times beta, 0 times beta. And this simplifies to beta alpha, and because 0th location has beta, so I can write it as beta times ket 0, and because my first location has alpha, so I write it plus alpha times ket 1. And you can see that this result and this result is exactly the same. So we have verified that this matrix behaves exactly like we have written here. Now let's clear the board and then we will talk about Pauli-Z Gate. Pauli-Z Gate is also a single qubit gate. So it takes a single qubit as input and produces a single qubit output, and it is also a unitary as well as Hermitian gate. That means it is inverse of itself. So if I apply two Pauli-Z gates in sequence, they will cancel each other effect and my input will become equals to my output. Let's write the matrix of Pauli-Z gate. So the matrix of my Z gate is 1, 0 and 0, minus 1. Now let's see what is the effect of this matrix. So if I apply Pauli-Z Gate on ket 0, my answer remains ket 0. It does not change. And if I apply a Pauli-Z Gate on ket 1, then I get a phase. So my answer becomes minus ket 1. We can also apply Pauli-Z Gate on superposition. Let's say I apply Pauli-Z Gate on superposition of alpha ket 0 plus beta ket 1. Then because of the experience that we have with the X gate, we can quickly take Z inside this summation and can apply Z on ket 0 and ket 1, and our answer will be alpha ket 0 remains the same, and here I will have a negative sign because ket 1 will become negative ket 1, so I will get minus beta ket 1. We can obviously verify any of this using this matrix. Let's verify this one. So what will be my result if I apply this matrix on vector ket 1? So here is my matrix, which is 1, 0, 0, minus 1. I apply this on vector ket 1. That means my first location has 1 in it because it is ket 1. And now I have to find my answer. I multiply this row with this column. 1 times 0 1 times 0 is 0, so I will have 0 here, and then 0 times 1 is also 0, so my answer will be 0. Similarly, 0 times 0 plus minus 1 times 1, so I will have here minus 1, and this simplifies to minus 0, 1, and we know that we can write it in a ket notation of minus ket 1, because here at the first location I have 1, so this is ket 1, and minus is outside, so my answer is minus ket 1, and we have verified this. If I apply a Z gate on ket 1, my answer is minus ket 1. Now let's look at another quantum gate. My favorite gate of all the gates is Hadamard Gate. I even like its name, Hadamard. It is a single qubit gate which is also unitary and as well as Hermitian, and its name is Hadamard Gate. The reason I like this gate is because all quantum algorithms use this gate. So to make it clear, I have made multiple videos about it, so you should go and watch those videos also. In this video, I'm going to just tell you this matrix and going to provide you a simple example. So the matrix of this gate is 1 over square root of 2, 1, 1, 1, minus 1. And this gate is used so often in all the circuits because it takes a pure state, and from that pure state it creates an equal superposition. So if the input of this gate is ket 0, then the output will be ket 0 plus ket 1 divided by square root of 2, and this output is also known as ket plus. Similarly, if the input of this gate is ket 1, then the output will be ket 0 minus ket 1 divided by square root of 2, and this output is known as ket minus. Now this gate is reversible like all the quantum gates because it is Hermitian, so it is reverse of itself. So if I put another Hadamard gate on this output, my result will be ket 0. So if I say, oh, I should say Hadamard gate here, not Z gate. Why I'm writing Z gate? So Hadamard, sorry, not Z gate. So Hadamard and Hadamard. So if I put Hadamard gate on input ket plus, then my answer will be ket 0 because this gate is reverse of itself. So it takes input ket plus and gives us output ket 0. Similarly, if our input of this gate is ket minus, then our output will be, guess, ket 1. We can obviously try this matrix to show that this matrix is working the way it's supposed to work on any of those inputs and outputs and see if the result is exactly like we claim. So let's try maybe this one. So I take my, once again, here should be H, not Z. Okay. So once again, I try the Hadamard gate on ket plus. So this is my Hadamard gate on ket plus, and ket plus is defined as ket 0 plus ket 1 divided by square root of 2. At the 0th location, we have 1 over square root of 2, and at the first location, we also have 1 over square root of 2, and if we multiply our rows and columns, we're gonna get 1 over 2 outside, because I can take this 1 over square root of 2 also common, so this 1 over square root of 2 and this 1 over square root of 2 multiplies to become 1 over 2, and inside I will get 1 times 1 plus 1 times 1, so it will 1 plus 1 here, and in this case I will have 1 times 1 minus 1 times 1, which is, so my final result will be 1 over 2 and 2 over 0, which is equals to get 0. So yes, this matrix works the way it's supposed to work. That means it takes a pure state and converts that pure state into a superposition. And we have multiple videos about it because this gate is used extensively in many different ways. So please watch those videos also. Now you will be wondering that if all the gates are unitary and if all the gates are Hermitians all the time, so the answer to this question is yes, all the gates must be unitary as I have explained earlier, but all the gates don't have to be Hermitian. So they don't have to be inverse of themselves. So example of such a gate which is unitary but not Hermitian is rotation gate. So this is our R theta or rotation gate. So this is unitary gate, like all the quantum gates must be unitary but not Hermitian. So this gate is not reverse of itself. If you have to find reverse of this gate, you have to take conjugate transpose of this matrix, then you can get reverse of this gate. So R theta is rotation into dimension, and this is equals to cos theta minus sine theta cos theta. So this matrix is not Hermitian because if I take transpose conjugate of this matrix, I don't get the same matrix. So in this case, my R theta is not equals to R theta transpose conjugate. But this matrix is unitary because if I take R theta and takes transpose conjugate and multiply with R theta, my answer is always equal to identity. So it will be an interesting quiz question to make you verify both of those things. Now let's look at the two-qubit gate like control gates and swap gate and etc. For that I must create the board first. It is time to look at many two-qubit gates. Now recall that we said that if we have a single qubit, then we need 2 by 2 matrices as quantum gates. And if we have n qubits, we need 2 raised to power n times 2 raised to power n matrices as quantum gates. What about 2 qubits? So if I have 2 qubits, then my matrices will be 4 by 4. Now let's look at a swap gate that takes 2 inputs and then swap them at the output. So this is my swap gate. And it takes 2 inputs and then it swaps those inputs. So if my input is x here and if my input is ket y here, then on the output my output will be ket y and ket x. This gate is unitary and Hermitian. The matrix of swap gate is as follows, that we have the first column of identity matrix and the last column of identity matrix, but the middle 2 columns are swapped with each other. So here I will have 0 0 1 0 and here I will have 0 1 0 0. So these kind of matrices are also known as permutation matrices, which are basically identity matrix but some rows and columns are swapped. So we can test this matrix on some input to see if it is really swapping the inputs. Let's try this, that I give swap gate input of ket 0, 1, then our claim that our output will be 1, 0. Now we verify that swap gate works this way using this matrix. So here I plugged in my matrix. And now I write my input here, which will be a 4D vector whose first location will have 1 in it. So this is my 0th location, this is my first location, this is my second, and this is my third location. And now I have to find the answer. A simple way to find answer is to write the first column. Because I have 1 at the first row of this vector, so my result will be first column. This is just a shortcut to find the result quickly. Or you can try to multiply this and the result will be anyway this column. 0, 0, 1, 0, and this is equals to ket 1, 0, because now my 1 is at the second location, so my result will be ket 1, 0, which is ket 2. There are some series of 2-qubit gates which are called as control gates. The one of those gates is CNOT gate, but there are also Controlled-Z Gate, Controlled-X Gate, Controlled-Y Gate, Controlled-Hadamard Gate, and so we can take a 1-qubit gate and we can create a 2-qubit control gate using that gate. Just let's begin with the CNOT gate and then we will see other control gates. So CNOT gate, which is also unitary and Hermitian, and its diagram is like this. First qubit is controlled and the result of first qubit is XOR with the second qubit. So if I have X here and ket Y here, then my output will be ket X, and here I will get ket X XOR with ket Y. The matrix of CNOT gate is once again a permutation matrix. Permutation matrices are always unitary and Hermitian. In this case, my last two columns are swapped. So the first two columns are of identity matrix, but the last two columns of identity matrix are swapped. So I will get here 0, 0, 0, 1 and 0, 0, 1, 0. That is my CNOT matrix, and we can try this matrix on any input to find out that this matrix works the way it's supposed to work. So for example, if I take CNOT gate and apply it on input 1, 0, because my control bit is 1, therefore this will change. So my answer will be 1, 1. So whenever my control bit is 1, the second bit is flipped. Now what about this case when my control bit is 0? Let's say my control bit is 0, then the second bit remains the same. So my control bit is 0, the second bit remains the same. So similarly, there are other cases, and I have a separate video about CNOT gate, so you should go and watch that video also. Now, there is an important thing that I want to mention, that we can make control gate out of any single qubit gate. So our formula of making control gate is as follows. But this formula works for big endian system. For little endian system, you need to write a different formula, but I like the big endian system. So let's say I want to make control U gate, where U is a single qubit gate. Then my matrix will be that first two rows will be of identity matrix, and here I will have 4 zeros, and then here I will have my matrix U. For example, if somebody asked me to make a Controlled-Z Gate, I know from the previous blackboard that my single qubit Z gate is equals to 1 0 0 minus 1. So if somebody wants me to make Controlled-Z Gate, then that will be CZ is equals to what? That the first two columns will be of identity matrix. Here I will have 4 zeros and here I will have Z matrix. So my result will be 1 0 0 0 0 1 0 0 and 0 0 0 0, and now here I will have Z matrix 1 0 0 minus 1. If somebody asks me to make Controlled-Hadamard gate, so how to make that gate? That once again, Controlled-Hadamard gate, I write first two columns of identity matrix is 1 0 0 0 0 1 0 0, and here I will write 4 zeros, and here I will write my Hadamard matrix, which is 1 over square root of 2, 1 over square root of 2. Now I can take 1 over square root common because it is only in these entries. So I have to write 1 over square root of 2 now. 1 over square root of 2 and minus 1 over square root of 2. So we have learned a swap 2-qubit gate, and we can make many controlled 2-qubits gate using this trick, and one of those gate is CNOT gate, for which we have a separate video. Although there are many other quantum gates, but I think for this video these many gates will be sufficient. See you in the next video.